Okay, we're on. We are getting where we are getting pretty regular due dates. So, looking at the schedule, things are lining up there pretty quickly. So we have an assignment due tonight. That is the second part of that algebra review. So that one's been posted for a long, long time. And I didn't look this morning at how many people had been working on that one. It was a substantial number as of last week, but not everyone. So if you're not working on that one, then now's the time, because that is due tonight at midnight. Okay? And so got to get that one done. And then we have our first quiz coming up, so that's going to be due on Wednesday. So this is just problems similar to problems in that algebra review part 1 and part 2. So that one is much shorter, okay? But that's a quiz now, remember, so the format is slightly different than the homeworks, okay? So so be ready for that. I think one of the major differences is you have to submit the entire quiz at one time, okay? So instead of just problem by problem. So anyway, but it's short. So once you have done the part 1 and part 2, then you still have multiple chances, 5 chances to submit it to improve your score, though, okay? So so that one's then due on Wednesday, and then we've got our 2.1 homework, which is due next Monday. So we're going to finish talking about that, I think, today, and hopefully get started with part 2, depending on how much progress we make here, okay? So that's kind of the schedule of events, and then as usual, right, the algebra review. So remember, I upped that to $10 for completing that with an 82. And that's not due until the first test, okay, which is 2 weeks from Wednesday, okay? So that's the sequence of events. So that's all pretty clear there. I added one homeworks over the weekend. This homework 2.2, that wasn't there before, so tentatively due on the 20th. So that's a Saturday. That's a little bit unusual, I think. Is that a Saturday? I think so. And so, because I wanted to push that back a little bit, but didn't want it to go into Monday, because that's getting close to Monday the 22nd, because that's getting close to the first test day. So anyway, that's new, but we'll probably start talking about that stuff today. And it's not difficult, but it's new, so so that may make it seem harder than it really is, but don't be intimidated by it. It's not that it's intrinsically difficult. It's just that it may be stuff that you're seeing for the first time, okay, as opposed to the algebra review. So don't forget, you can take advantage of John. He can even help you with the quiz. And also, people were asking about additional times. So you can also go on Wednesday, did I say this, at 3:15 to 4:15, or also on Tuesday, that's Tuesday, from 11:30 to 12:30 if you cannot make it immediately following class, and then always on Friday from 12 to 5 p.m. If you want to go to South 405 and get tutoring help. You can also go to North 925. I don't know where that one's listed here on here. North 925. But North 925, that's the math center, but you won't get the bonus points for going there, because you don't have that set up yet to record you. So so this is where you can go for the calculus currency. But you can still go get help in the math center, which is, I didn't list it on here, but that's North 925, right? And that has lots of, I need to add an announcement about that. So that has lots of hours, though, okay? So that's open during weekdays and also on Saturday afternoons. Yes. If you go to South 405, I do know, okay, because right, okay, because they're giving me a list, all right. So, but I only see that like once a week, so it may take a little while to get the. Yeah, well, yeah, because when you go in there, they'll have you check in. Yeah, okay, right, okay. But in the Math Center, which is North 925, you do have to check in there as well. But I don't have a way of finding out whether you've gone or not. Okay, so that's why I can't give you the extra credit for that one. All right. All right. So back to the homeworks there. Do we have any questions about, since it's coming up due tonight at midnight, any questions about the part 2 in particular that you want to ask? That you need to ask? Uh-huh. Let's see if we can figure them out. Which one? Number 3. Yeah, so that is usually, let me see if they, yeah, so usually when you're given a function, so it can be in the form of a graph or it can be a formula, right? So most frequently you'll get a question like this one where you're given an input and you're asked to evaluate the function at that input. So that means find the output that matches that input. So that's all very straightforward, right? Okay. Huh? That's right. But this one is backwards. Exactly right. So you're given the output and you're asked to find the matching input instead. Okay. Yeah. All right. So and so both ways are important to know how to do. And so. But usually you see this one more frequently. So to answer this one, so we want to find the values of x, and it can be more than one value. Now, when you're given an input, right, and asked to find the matching output, right, the inputs always go inside the parentheses. So you know these are inputs, and we're asked to find matching outputs. Then you're only going to find one answer in every case, okay? Because that's what makes a function, right? Every input just matches one output. But when you're asked the question backwards, if you're given the output, there may be multiple inputs that match that output. So you may have multiple answers, okay? Well, it says there, enter your, yeah, that's what it says. So enter your answers as a comma-separated list, right? So let's see. So to answer this one, what you would do is instead of going along the x-axis, right, because that's where the inputs are plotted, right, you will go to the y-axis because that's where the outputs are plotted, and you're going to find 2, right? And then you just go left or right until you, until you hit the graph, and then you find the matching x value. So it's pretty clear here, right? One answer is -3, right? If x is -3, then h of -3 is 2, right? Another one is 2, right? Okay, because if x is 2, the matching output is 2. And then the last one there is 4, okay? So if x is 4, the matching output also is 2, yeah. And so, so you just are supposed to type them in there as a list, right? Okay, so let's try it there. So what do we say? -3 was one of them. And is it typing? No, yeah, so -3 and 2 and 4. Okay, yeah, all right. So so if we submit that part, right, we should get that one right. All right, so that is now slightly new, okay? So that was a little bit unfair question there. on part 2, because we just started talking about that. So that's really covered more in 1. All right, okay. So it says find the net change in the function, net change or just change, right, in the function between x equals minus 3 and x equals 3. Okay, so we're just getting ready to see an example like that to start the notes today. Okay, but the formula for net change when you're given a function represented by a formula. Okay, so this is first thing in the notes, but let me write it down there. Is you're going to take the function at the last input that you're given, evaluate it, okay, find the matching output, and then subtract off the matching output at the first input that you're given. Okay, so the formula looks like this. In this case, the name of our function is f, however, I'm sorry, is h. Okay, so in this example, we will calculate h of x2, which in this case is 3, right? Okay, and we'll subtract off of that h of our first input that we're given, which is minus 3. Okay, so to find h of 3 and h of minus 3, you have to, of course, look at the graph, right? That's just evaluating the matching output. So let's see, what is the h of minus 3 was 2, right? Okay, because we just found that out in the previous answer, correct? And then h of 3 looks like, what's h of 3? Is that 3? Pretty close to 3. So it looks like here the net change is 1. Okay. Mm-hmm. Uh-huh.
It has to do with like years, something like with years. Keep going up a little bit more. I think it's that one.
This one?
I think so, yes. Or go a little further down.
Yeah.
No. So just go back to the other one because we're. I think it was the one he was just. Yeah. It's like 19 something. I think it was like 9. There, that one.
This one?
Yes.
That one's bothering you?
Yes, very much so.
Okay. All right. All right. So let's see. Is it just? Can I ask what's?
Well, I guess you can say it's hard for me to read the graph, and when it asks for like, I'm just confused.
Okay. So this is about direction. Okay. So where a function is increasing and decreasing. Yeah, I can't. Sometimes the graphs are hard to read. So this one I thought would be pretty easy. Okay. So it says. So here's a function named f that's graphed here, and it says. If f is increasing on an interval, then the y values of the points on the graph, and then we get to select, right? Okay. So if it's increasing, the y values are going to go what? Up, right? Okay. Yeah. So the y values are going to rise as the x values increase, right? Okay. From the graph, we can see that f is increasing on which intervals here, okay? And we want to enter our answer there using interval notation, okay? So again, you want to look there from left to right, okay, along your x-axis, right? Okay, you want to look from left to right on your x-axis, and where the graph is rising, that's going to be the intervals where it's increasing, okay? So at first, the graph is indeed rising, right? Okay. And that apparently happens what? From negative infinity all the way out to what? 2, right? Okay, to 2. And then it's falling for a little bit, okay? But then right here it starts rising again. So it's so the function is increasing again from what? 4 to 5, right? Okay. But remember, you're giving your answer always in terms of the x-axis, okay? So don't give your answer in terms of the y values. Although it's the y values that are increasing, give your answer in terms of the x-axis. So if I type this in as an interval, well, let me do that. What am I looking for here on my palette, by the way? So I'm used to the palette appearing over here. So is that new? So what do I have to go to sets?
Are you looking for infinity?
Yeah. Oh, it's in symbols. But do I need to start with? Oh, I can type it from the keyboard. Thank goodness. Okay. All right. So that's easy. All right. So we would start there, right? Okay. And then it's in symbols, right? So I've got to type in minus infinity, though. Oh, did it let me do that? Or did I do something bad there?
I think you shifted.
I think I shifted. You're right. So let's go back. Okay. So minus infinity, and then, now I've forgotten my answer. Was it 2? Yeah. Okay. To 2. Okay. Yeah, but let me close that first, right? Okay. Oh, I had it closed. All right. So no, go back to sets and put the union in, and then it's going again from 4 to 5. Ah, okay. So that's where it's increasing. Is that your question? Does that make it clearer?
Yeah, it's just a problem. I don't see it on here.
Oh, okay. All right. All right. And then I guess this is where it's decreasing, right?
Yeah.
So the graph is falling, and that's going to happen really from the other part of the domain. So that would be 2 to 4, and then 5 to from 2 to 4, and then 5 to infinity, right? Okay. So I wonder if we got that one right. Yay! Okay. So we can read that one. What? 4b. That one's tricky. Okay, so they want us in 4b now, just looking at the graph, to write down the domain and the range, okay? And so the domain now is the set of inputs, right? And many times that's all real numbers, so that's negative infinity to infinity, but not on this graph, because this graph has a distinct beginning point and an ending point, right? Okay, so the domain starts over here where the graph starts, and so that looks at minus 4, right? And the domain is going to continue over here till 2, right? And there's a break in the graph, but 2 is part of the domain, okay? 2 is definitely part of the domain. The matching output for 2 is 3, not up here at 5, okay? That's why we have the open circle there and the closed circle here to indicate that, oh, the matching output is really 3, it's not 5, okay? But when you get a little bit to the right of, not 3 there, but 2, right? Is that 2? Okay. But when you get a little bit to the right of 2, notice the outputs shoot up there quite, and then you have much larger outputs for this piece of the graph, at least for a little while. So anyway, so the domain does include 2, all right, and extends over to 4. So altogether, your domain goes from minus 4 all the way over to Is that 4? Yeah. Okay. Oh, you're talking about the quiz? Okay. All right, okay. So we all see the domain there, -4 to 4. And then the range now is the set of output values. So let's see, what output values do we get here? What's the smallest output value? 0, right, because the graph dips all the way down to 0. And what's the highest output value? Not 3. Yeah, actually all the way up here at 5, right? Okay, because you do have an output there at 5. Not here, because that point is not really on the graph. That's why we have an open circle. But you do over on this side, you do have an output of 5 right there, okay, because the input of -4 gives you an output of 5. So the range is really 0 to 5, including 0, I think, and including 5, okay? All right? On the quiz, all right, so we'll look at that in a minute, okay? All right, did y'all find other questions there on the, is it 20? So that's the last one, so maybe that's the hardest one, right? Okay. Uh-oh. Yeah, okay, that's just a pure algebra problem. All right, okay. All right, so here we want to add or subtract, right, these fractions and then simplify our answer, okay? So no real surprise there that that one causes a little bit of issue. Because you got to remember how to add fractions with, in this case, different denominators. If all those denominators were the same, then it would be fairly easy to add those fractions, right? Because all you would do is add or subtract. In this case, add, right? Because this is all addition. Just add the numerators together and keep the common denominator. But here, all your denominators are different. So in order to combine these fractions, you're going to have to find a common denominator, okay? So you've got to figure out a denominator you can use to add these fractions together. So what denominator can we use to add these fractions together? What would be, there are many possibilities, but what would be the easiest one, okay? So by a common denominator, I mean, is there some expression that you can transform each of these denominators into rather easily so you can add these fractions all together? It's what? Yeah, I've heard x cubed, and I also heard x to the 6th. Actually, either one of those would work, okay? But the easiest one is going to be x cubed. You see that, Zaman? Okay? You can use x to the 6th, all right, power to add the fractions together, but x cubed also would work, and that's a little bit simpler denominator. So I'm going to use x cubed as my common denominator here, okay? And the reason that was nice is because, see, this fraction already has x cubed as its denominator, so you don't have to transform that fraction at all. But you do need to work with these two fractions so that they'll have a denominator of x cubed, okay? So that you can add all the fractions together. See, that's the rule for adding fractions together, right? Is if they all have the same denominator, you can add them together just by adding their numerators. All right, so let's look at the first fraction. Here we have 1 over x. So we want to transform that fraction so that its denominator becomes x cubed. But you don't want to change the value of the fraction. If you change the value of the fraction, then you've changed the problem, right? Well, the easy way to think about this is, okay, what do I need to multiply into that denominator so that it will become x cubed? Because x cubed is what I'm going to use as my common denominator, all right? So what can you multiply x by in order to get x cubed? X squared, right, okay? So I'm just going to multiply the bottom there by x squared. But look, if you just multiply the bottom by x squared, you've changed the value of the fraction. And see, that you don't want to do, because that means you've changed the problem. So what you're going to do is actually multiply the top and the bottom by x squared, you see, okay? That trick will work, because x squared divided by x squared is really 1. So you're really not changing the value of this fraction, this first fraction in the sum. You're not changing its value because you're really just multiplying it by 1. So you're going to make it look different, but it's really going to have the same value. All right? What about the second fraction now? So see, now it's x squared, but again, I want it to be x cubed, right? So I need to multiply something into that denominator to make that x squared into x cubed. And of course, it's obvious what that is. In that case, it would be what? Just x, right? If you multiply x times x squared, you're going to get x cubed, correct? But again, so that you don't change the value of the fraction, multiply top and bottom by x. X over x is really 1, so you're really multiplying that second fraction really by just 1. You're not changing its value, so we're not changing the problem. And now the last fraction, well, we don't have to do anything with that. That's nice, because it already has our common denominator of x cubed as its denominator, you see. All right, so let's see now, what do we get here? So I multiplied the first fraction by x squared over x squared. That gives me x squared over x cubed, correct? Right? Just multiply x squared times 1, that's x squared. X squared times x is x cubed. Easy. What about for the second fraction now? Well, again, you're going to get x cubed in the denominator. That was by design. And we multiply x times 1. Of course, that's just going to be x, right? So that's x over x cubed. And then finally, last fraction, we didn't change that. Now those fractions all have a common denominator. So now I can just keep that common denominator of x cubed as my denominator and just add the numerators together. So you get x squared plus x plus 1, okay, over x cubed. And that's it. Now, you might be able to, at this point, reduce your result, because notice it does say it wants you to simplify, but to simplify, you would have to factor the numerator, x squared plus x plus 1, and then try to divide out common factors. But I don't think x squared plus x plus 1 is going to factor. You can try factoring it, but it won't factor. And so that's it. Okay, you're not going to be able to reduce your answer at all. Do not divide out the x squared with the x cubed, or the x with the x cubed. Okay, you cannot divide those things out. Okay, one thing you have to remember, to reduce a fraction, there might be a reducing a fraction in an earlier problem here. To reduce a fraction, the numerator has to be factored and the denominator has to be factored. Then you can divide out common factors. But this numerator is not factored. Okay, that numerator is not factored. All right, and I don't think I can factor it. So that's it. That's our final answer. Is that hard to type in? Okay, now I know I can do that, right? Is that right? And then I come up here. Can I get up there? Was that I thought that was a fraction bar.
No.
Oh, no, this is a fraction bar, right? Oh, it's easier just to type it? Yeah, there is a fraction bar. I just looked at the wrong thing. So there's a fraction bar, right? So if I do this, will it... oh, nice. Okay. So it's x squared, okay, plus x, and then plus 1, and all of that then divided by x cubed. So if you use the caret key, it'll give you the exponent. That's just like in Desmos. Before we submit that, let's see. Oh, here is one now where it says simplify the rational expression. Rational expression means fraction. So they want. I'm looking at 18. They want us to simplify that fraction. Okay, so we're not adding or subtracting. We just want to reduce that fraction. So to reduce that fraction, if you've forgotten how to do that, it's just what I referred to a moment ago. To reduce that fraction, you can't just start canceling things in the numerator and denominator. That's very tempting to do. So it's very tempting to think, oh, I can divide out this x squared with this x squared, okay? Or maybe this 2 divided by this 1 or something like that, right? Okay? But you cannot do that immediately. First, you must factor the numerator and factor the denominator. So let's see. Can we factor x squared minus x plus 2? That will help. Okay. So x squared minus x minus 2. Okay. And all right. So let's see if we can factor that numerator. And I think it does factor, right? I think it's going to factor as x minus 2 times x plus 1. Okay, just try that. X times x is x squared. Minus 2 times plus 1 is minus 2. So we get those two terms right. And then for the middle term, we have minus 2x, right, plus 1x, minus 2x plus 1x is going to be minus 1x, right? So we got the numerator factored. What about the denominator? That's a famous way of, that's a famous factoring form. How can you factor x squared minus 1? Yeah, that's called difference of two squares. Remember that? Okay. This is a perfect square. 1 is a perfect square. So you can factor that as the sum of the two square roots times the difference of the two square roots. Square root of x squared is x. Square root of 1 is 1. So you can factor x squared minus 1 as x plus 1 times x minus 1. Now, is there something we can divide out? Yeah. Now we can divide out the x plus 1, you see. Okay? So you factor first and then divide out common factors. That's how you reduce a fraction. Okay? Just don't go willy-nilly and start dividing things out of the numerator and denominator. Make sure they're both factored first. Let's see if we got those two right. If I can get that typed in there. Okay, so let's see. There's my, I'm learning this. So it's what, x minus 2 was at the top? And then x minus 1. Okay. All right, so let's submit it there, and okay, well, I still remember that, and I remember that too. Okay, nice. Okay, all right, so that's a little, that's just totally algebra practice there, but that's why we had those problems incorporated into the algebra review, just to remind you of some of these things. Okay, all right. I'm going to go to the review. What, you have another one on the review? Okay, all right. Let me see if I go backwards here. Well, that's going to take a while. All right, so let's look at this one, the quiz. And finally now, at last, okay. Whoa, yeah, okay. I see why that one is bothering you, okay. All right, so the population, actual and predicted, of Alaska, X years since 2000, can be modeled by this formula. So apparently the output from this formula is people, it measured in thousands, and the input here is elapsed years. So one of our favorite inputs here, it's elapsed years since 2000, right? Okay, and so the question there is, what's Alaska's population expected to be in my version of the problem? It's 2019, so you might have gotten a slightly different version of the problem. Okay. All right. Well, that one is pretty straightforward, right? Okay. Except for maybe the arithmetic. All you have to do is evaluate this formula with a particular input, right? And what input would you use there? Ngozi, what input do you use for my version of the problem? Okay, I think you're describing to me how you did the calculations versus just what I want to fill into the parentheses there. Okay, what do I put in the inside the parentheses here, Ngozi, in order to find the population in 2019, notwithstanding how we're actually going to do the calculations, right? Okay, so what do I put in the parentheses there that would give me the population in 2019? Right? So look at the description of the problem. It says X, right, is the number of years since 2000. So 2019 would be how many years from 2000? 19, right. So what I'm going to calculate here is A of 19. All right, okay? In other words, I'm going to plug 19 in for X into that formula. So I get that 0.638 times 19 squared, and then plus 6.671 times 19, and then plus the 627.619. And so with your calculator, you're going to have to do all of that ugly arithmetic, okay? And then don't forget, at the end of it, be careful because the outputs from this formula are in thousands. So I bet when you fill in your answer, you have to convert that to thousands, okay? All right. Let me show you now. Let's do the arithmetic, but I'm going to show you my lazy way of doing the arithmetic because I'm going to use the Desmos calculator to do the arithmetic. Okay, so I went to www.desmos.com, and it's really great at doing arithmetic. Now, you will have to type in, you are going to have to type in all the numbers, so that's, no way to avoid that. Okay, but that's life, right? Okay, so we can't get away from everything. So it's what, 0.638, right, times, and you can, use the keypad down here, right, to do the, yeah, you can use parentheses too. I think it will respond to that, okay? And then we're going to square that. So I just use the a squared key, okay? So there's the 0.639 times the 19 squared, right? And then plus, and then what's the next part there? 6.671. So 6.671, and I guess you can type that off of the keypad too if you want to, or off of the keyboard, times the 19, okay? And then don't forget, though, you've got to type in the last part there, which is the plus 627, what is it, 0.619? 0.619. Let me move that out of the way. And the nice thing there is, you see Desmos will give you your result, right there as you're typing stuff in, okay? So it looks like 985.047, but now we're going to convert that to thousands. So if you multiply that by 1,000, you just get what, 985,047, okay? So let's go back and see if that no. Yeah, okay. So I don't think we have to enter the decimal point here, okay? Because notice it says afterwards people, right? Okay? And you're not going to have a decimal point of a person, right? So there's the 985,047. Okay. All right. That's the pretty straightforward part. Okay. Yeah, it really is part B, right? That's the ugly part, right? Okay. All right. So it's now there it is. When is Alaska's population expected to reach 840,000? Okay. And it says round your answer there to 3 decimal places. Okay. All right. So that one is that's the hard part. Okay. All right. How do we answer that question? Yeah, see, this is an output, right? Okay, so notice they're giving us, see, in this problem, they gave us an elapsed year. Well, not an elapsed year, but they gave us a year, right? Right, so that's an input, and they ask us to find the population. So we plugged the 19 in for X and found the population. But here they're giving us a population and asking us to find the X. So we're going backwards. So what you're going to do is plug in the 840,000 in the appropriate form for the output, okay? And then you're going to have to try to solve for X, okay? Then you're going to have to try to solve for X. All right, so let's see if we can do that then. So let me just slightly adjust this. There was the formula with the 19 plugged in for x. But remember the original formula. Here we had x squared and here we had x, right? And so that was the formula for a of x, right? Okay. But they're telling us what our output is going to be, right? They're telling us the output is going to be 840,000, right? But now remember, our outputs in the formula are measured in thousands. Okay, so we're not going to plug in actually 840,000 for the output. What do we plug in for the output there? 840, right. Okay, what we'll actually plug in is 840. And now we're left with, the ugly task of solving that ugly equation. Okay, so you have 840 is equal to this. And now we have to figure out how to solve that equation. That is a quadratic equation. Okay, that's a quadratic equation because the unknown there, x is squared. And normally we would try solving quadratic equations by using the F word. So we would do what? Factor. But, with all these ugly decimals, right, there's no way we're going to be able to factor here. So we have to resort to plan B, and I would say plan B is going to be the quadratic formula. So we've got to remind ourselves here of the quadratic formula. I don't think I've talked about that in class yet, but you've seen the quadratic formula before, so we've got to practice that a little bit here. Right? To use the quadratic formula, though, first you've got to set the equation to 0. So I've got to make one side of the equation 0. So I'll do that by subtracting the 840 from both sides, you see. So I'll have plus 627.619 and then minus 840, okay? So y'all help me here. What's 627.619 minus 840? And give me all the decimal places there, because I think I'm going to need them all. What? 212.381. Okay, that sounds convincing. Okay, so I think that's right. So there we have 0 is equal to the 0.638x squared, the 6.671 times x, and then the minus 212.381. Right? Okay, so we got it set equal to 0. This is a pretty standard quadratic equation, except what's ugly about it is you've got these ugly coefficients with all these decimal points in it, right? Okay, so that messes up the factoring, so we're going to have to use the quadratic formula. So let's see. Let's remember now, what does the quadratic formula tell us then the solutions to a quadratic equation like this are? Okay, well, here it is. Okay, it's going to be minus b plus or minus the square root, here's the famous quadratic formula, minus 4 times a times c, all of that divided by what? 2a. Okay. And remember, the a's, b's, and c's, those are the coefficients of the equation when it's set equal to 0. So, and this one's set equal to 0. So that's the a, that's the b, and that's the c we're going to substitute into our quadratic formula. Okay? All right? So we have there that x is equal to minus the 6.671, okay, plus or minus, because you may have two possible solutions here, but I think one of these will probably end up being negative, so that won't be useful to us, okay, and then the 6.671 squared minus 4 times, it's going to be hard to squeeze all of that in. Okay, let me write it down here. Okay. All right, so we have x is equal to the minus 6.671. Okay, plus or minus the square root of the 6.671 squared minus 4 times the a, and the a is that 0.638, right? And times the c. And the c is that minus, be careful about that, 212.381. All right? So the c is negative here, so be sure you get the signs right. And then all of that divided by the 2 times the 0.638. okay, which is the A. And all of the rest of this now is just the arithmetic of simplifying that big, ugly expression, okay? All right, let's see if we can do that in Desmos now. Now, the plus or minus gives you, the reason you have the plus or minus here is you've got two possible solutions. One of them is this first constant plus that square root divided by the 2 times a, and then the second one is this constant minus that square root divided by the 2 times a, okay? So you need to look at both of them. Probably one of them will come out as a negative value, and since x here, remember this is x, and x is elapsed years, so since x is time, the negative won't have any meaning to us, right? Okay, so we're probably interested in the positive one, but I'm not sure yet. So let's try the Desmos there again and plug all that in there, okay? So you can do this with a calculator as well, right? All right, so let's see. Minus 6.671. Okay. And then let's try the plus first. Okay, plus, and then we have square root. Let's see if I can get a square root in here. Okay. So there's a square root, right? Okay. So the 6.671 squared minus the 4 times the, what's the a there? 0.638. And then times, and let me put in some parentheses here around that negative there, although I don't know it's really necessary. The minus 212 point, what is that, 381? All right, so that's all the numerator, but remember I have to divide all of that by 2a, right? Okay, so let's try dividing that by 2 times the 0.638. Okay. And there it tells us, there's our answer, which is, if we typed in right there, 13.75, okay? And so if we, 751, that's right, okay? All right, so let's see if we got that right. So it will take 13.751 years after the end of 2000. So this will occur in, wow, what is 0.751? That's 3/4 of a year, right? So would that be September? Is that 2013? 20. Yeah, mine's slightly different, right?
2013.
Now, we got to.
Is there like an actual way to precisely calculate that? So, I guess.
We have to be a little bit careful here because this says after the end of 2000. All right, after the end of 2000. So, how much more precise do you want? This looks pretty precise to me, George. Okay, right, okay, yeah. You mean the September?
Yeah.
Yeah. Well, the 0.75 was 3/4, right? How many months are there in a year? 12, right? Okay. What's 3/4 of 12? It's 9. So I was thinking September, okay? But maybe we're off by a little bit there, October, okay? But we have to be a little bit careful about the year because this is starting at the end of 2000, okay? So at the end of 2000. So 2001 is the first year. Let's count off here. So there's the 2001 is the first year, 2002 is the second, 2003 is the third, 4, 5, 6, 7, 8, 9, 10, 11, 12, Oh, that puts us at the end of 13, right? So doesn't this go into, yeah, I think this goes into September of 2014, okay? I think we actually, since we started at the end of 2000, this is really putting us into September of 2014, okay? Let's see how close we got. Okay. Well, we got the hard part right, okay? So that's comforting. What did I do wrong here?
You were kind of wrong because I got
984 points. Oh, okay. I must have typed in a decimal wrong there, right? Okay. 686. Let's try again there. No, this was the part that was, okay. Yeah, so I typed a decimal in wrong in Desmos there. Okay, on that. Oh, but we got September wrong? So is that actually coming to, it's probably going to be October? There we go. Yeah. Okay. Because it was 0.751, so it actually bled a little bit into October, right? Okay. When it finally got to that 840,000. Yeah.
I have a question.
That one's really tricky. Okay. So I think I'm not going to. Okay. Look, on a test, I'm not going to ask you this part for sure. Okay, right? I'm more interested. That's the key thing there, right? Okay. I think this is just kind of. Well, I'm not sure why that's necessary. All right. Okay. I think they're just trying to torment you there a little bit there to figure out exactly what month that was. Yeah.
I was just asking why you didn't leave the 840 as 840,000.
Because notice it said this is the population is given in thousands. Okay, yeah. Yeah, so you have to read very carefully there. Yeah, the units of measure on the input and the units of measure on the output. Yeah, that one is often very tricky, and the only reason that they've made that conversion is to make the numbers a little bit smaller and easier to work with, right? Okay. See, this would have been this equation would have been that much harder to deal with if you had had a big, 3 extra digits there added in. So we just changed the measurement to thousands instead of just regular people. Okay. All right. Other questions there? Did that help? A little bit? Gerard, do you understand how we got to October?
Yes.
Sort of. Okay. All right. All right. Yeah. What's really tricky there is, to me, is the fact that you're starting from the end of 2000. Okay. And so you have to actually go into 2014. I would have probably started by I think I did put 2013 there, right? Okay. Not paying attention to where we started. Okay. All right. Let's go back to our notes now. So last time we got a few minutes here. Let's add one more example. Okay. So last time we were talking about 3 ways of measuring change. Scrolling it back there really fast. Remember, there's just net change, or what I often just call change, right? Okay. So that's just last value minus first value. All right. This is when we're measuring a quantity. Okay. And the quantity is changing. If we just want to measure change, that's just the last measurement of our quantity minus the first measurement. But more frequently, we will measure change as percent change. And so here's how you measure percent change. That's the last measurement minus the first measurement divided by the first measurement, and then you convert that to 100%. Okay? Or what we call the average rate of change. all right, that's the last measurement minus the first measurement. So notice both percent change and average rate of change involve change, okay? But in the average rate of change, you divide by the length of the time interval over which you're observing the quantity, okay? So change is important because it's incorporated into the percent change and the average rate of change formulas, but in most applications we're interested in either measuring the percent change or the average rate of change, all right? So we looked at a couple of examples of measuring the change and the percent change and the average rate of change in Amazon.com's fourth quarter revenue. Okay, that was our first example. Now, since we're going to be often working in the context of functions, okay, here are these same formulas converted to functions, okay? So if x1 and x2, okay, are input values for a function, and you have to assume that x1 is less than x2. So x1 is the first value and x2 is the last value. If you want to compute the change in the function outputs, or we just call that the change in the function, all right, from x1 to x2, okay, then you just calculate the output of at x2. That's your last value in your change formula, and you subtract off the output at x1. That is the first value in the change formula, okay? So really this is just the change formula, all right, last minus first, translated into the context of functions. This is the output value that matches the last input. This is the output value that matches the first input, okay? And if you want to calculate percent change, right, very similar idea. You just take the change, which is f of x2 minus f of x1, right, and then you divide that by your first output, okay, which would be f of x1, and convert that to a percentage by multiplying by 100%. And then the average rate of change is, again, just the change. So you calculate your change in outputs, so f of x2 minus f of x1, divided by the difference between your inputs. So in other words, the length of the interval between x2 and x1, okay? Notice this formula looks very familiar to you already, okay? Because you can rewrite that f of x2. If you don't want to write that in function notation, you can write that as y2, okay, meaning the second output. And you can write the f of x1 as y1, meaning the first input. I'm sorry, the first output. And then your formula looks like y2 minus y1 over x2 minus x1. And that formula is already familiar to you because that formula is the same as what famous formula from algebra? That's the formula for what? Begins with an S. Slope, right. That's the slope formula, exactly. So really, average rate of change is really the slope in disguise, okay? All right? Average rate of change is really the slope formula in disguise. All right, and that's an important fact to remember. All right, so let's apply that in an example. So it says the following function gives the typical yearly wage gap, okay, not the wage, but the gap in wages between male high school graduates and other male workers, okay? And the input here is elapsed years after 1990, okay? So there's a gap, okay, in wages between men who just graduate from high school and other male workers, okay? And that's what this formula calculates for us, is what that wage gap is, okay? All right? So first question is, what is the change? In other words, what is the change in that wage gap from 1990 to 2015, and then we just want to interpret that, okay? So once we get the answer, We just want to interpret that. Okay. All right. So this is just we're going to use the net change formula. All right. We're going to use the net change formula. So what is our x2 here? What's our second input? We're going from what's our second input here? Yeah, that's 2015. Now, however, remember, we're measuring our inputs in elapsed years. So we're not going to use 2015 as x2. Instead, we're going to count 2015 in elapsed years from 1990. So x2 would really be what? 2015 is how many years from 1990? 25, right. So our x2 is really 25. And again, the reason we do that is just to make the numbers smaller. Okay. All right, so that we won't be dealing with calendar years, which are big numbers, right? We're going to use elapsed years just to make the values a little bit easier, okay? All right, so what's x1? What's our first input value? Okay, so where are we starting at, in other words? Well, that's 1990, right? Because that's what we're told in the problem. And 1990 is how many elapsed years from 1990? 0. Okay, yeah. So our x1 here is 0. Okay? And so the change, according to that change formula, is just, well, you can't see that change formula, but it's easy to remember. It's just f of x2 minus f of x1. All right? So now I've got to do a little bit of arithmetic here because I've got to plug my my x2 and my x1 into my actual formula here. So remember, x2 is 25 and x1 was 0. So we've actually got to plug these numbers into that function, right? And do the arithmetic to finish this computation. Well, the f of 0 is really easy to do, right? Okay, so I'll do that one. If I plug 0 into this formula for x, what am I going to get as the output here? 3,500, right? Okay, because that term is just going to disappear. You'll have 217 times 0. So that part is easy. What's a little bit harder, but not too much harder, is plugging the 25 in. So that would be 217, right, times 25, correct? And then plus 3,500. So that is the f of 25. All right? See, I plugged the 25 in for the x, so I got 217 times 25. And then don't forget, in this formula, you're always adding 3,500, right? Okay, so all of this is the f of 25, and of course this is the f of 0, because when I plug 0 in for x, 217 times 0 is just 0, so all I'm doing is going to get 3,500 out of that, right? So this minus sign and this minus sign are the same, right? So all of that was the f of 25, and of course this is that's the f of 0. Well, some of this is pretty easy to simplify because there you have a plus 3,500 and there you have a minus 3,500. So that's going to just cancel each other, right? So all you're going to end up with here at the end is just whatever the 217 times 25 is, right? So what's 217 times 25 for somebody who has their calculator out? I'm pretty good with arithmetic, but not that good. What? 5425? Okay, no. All right. So there it is. The change from 1990 to 2015 is 5425. Okay. So how would I interpret that number? Okay. Well, that would tell us what? From 1990 to 2015, right? Okay, the gap in wages between just a male high school graduate and other male workers, increased by what? $5,425. Okay, so whatever it started at in 1990, okay, I'm not sure what it started at in 1990, okay, but by 2015, right, it had increased to not two, but it had increased by $5,425. Okay, so the wage gap increased over that time interval by this amount. Okay. Actually, we do know what the wage gap was in 1990 because that was f of 0. So in 1990, there was a wage gap of $3,500. And then by 2015, that gap had grown by 5,425. Okay, not grown to 5,425, but it actually increased by that much. Okay, so there was a much bigger wage gap in 2015 than there was originally in 1990. Okay, so that tells us what things are getting a little bit worse for people who just graduated from high school, right? Okay, they're falling further and further behind in their wages. Okay. Good thing you're here in college, right? Okay, so you won't have to be dealing with that wage gap. All right, so what's the average rate of change then from 1990 to 2015? Okay, so what's that average rate of change formula? Remember, it's just the change, right? So the average rate of change is just the change, and then what do you divide that by? So you take the change and divide it by what? Yeah, the length of the interval. So what's the length of the interval here? 25, obviously, right? So you just take your change and divide it by 25. Well, we already calculated the change a moment ago, right? Okay, what was the change? 54.25, right? And now we're just going to divide that by 25. And no big surprise there. What does that turn out to be? 217, right, okay? It turns out to be 217. Well, that's kind of a letdown, right? It turned out to be 217, which is the same as what? This coefficient. Well, of course. Why is it the same as this coefficient? Because what sort of function is that? If you make a graph of that formula, what sort of picture are you going to see? You're going to see a straight line, right? Okay? You're going to see a straight line, and you know that this coefficient of x in your formula for a straight line is always the same as what? What's that called? Begins with an S again? That's called the slope, right? Yeah, that's the slope. Okay. And I already told you average rate of change is the same as what? Slope, yeah, okay. So no big surprise there. We ended up with just coming out as 217 because that we already knew was the slope of this line, okay. Remember, if you have a function whose formula looks like this, whose general formula looks like this, where you have a coefficient that's m times x plus a constant, right? Anytime you have a function formula that looks like this, that's going to be a linear function. That's going to be a linear function. So you see, this is a linear function, right? Okay, and what is this coefficient always? We just said it. It's what? That's the what? That's the slope value, right? Okay. By the way, what is the b? What's the significance of the b? Remember what that number is called? That's the y-intercept. That's where the graph is going to cross the y-axis. Okay? All right, so no great surprise here that our average rate of change turned out to be the slope because the average rate of change formula is really the same as the slope formula. All right? Now, how do you interpret that number, though? If I ask you to explain the meaning of the 217, how would you explain that to me? So that's really the harder part here. It's not calculating the average rate of change, but if I ask you, okay, what does that number mean? Or if your grandmother asked you, okay, what's that number telling you? How would you explain that to grandma or me on a test? Okay? So what's the proper interpretation? So what's the 217 telling you? What's its practical significance? Right? This is what's really important. Okay? All right, so we got into this a little bit last time. Okay? So on average, right, from when to when? Yeah, from 1990 to 2015. Okay? What's changing? So what does this formula measure?
What's that called that we're measuring here? The wage gap, right, okay? So the wage gap is it increasing or decreasing? Yeah, it's increasing, right, because this is a positive number, correct? So it's increasing by $217 every year. That is really important there, okay? You've got to add that in per year. Yeah, every year our wage gap is increasing by $217, okay? On average, that's what's happening, all right? Don't leave off the per year, because see, if you leave off the per year, you look like you're saying that the wage gap has just increased by 217 over this time interval, right? But that wasn't correct. It actually increased by a big amount, right? Okay, it increased by $5,425. It just increased by 217 per year. That's what that number is telling us. Okay, here's an easy one now. So I'll let y'all do this one to finish it. Okay. So we had a question about men, but I don't want to be sexist here. So here's a question about women high school dropouts. Okay. All right. So this doesn't apply to you, thank goodness. All right. So it says the following function. What kind of function is this again? That's linear, right. That one is linear again. Okay. So in these two examples, I'm working with the easiest type of function. It's linear function. How do I know it's a linear function? What's the slope here? I've got it written, the terms in kind of a different order, but what's the slope? Be careful. Okay, yeah. I've got the terms written in opposite order here. Yeah, the slope is always what's multiplied by the x. All right. So the slope here is, yeah, the minus 0.22, right? Okay, and this is the b value. All right, that's the b value. That's the y-intercept. All right. All right. So it says the typical life expectancy for female high school dropouts. Okay. Well, this is what that formula is giving you. X elapsed years after 1990. Okay, X elapsed years after 1990. All right, first, calculate for me f of 0. That's so easy. Okay, so easy. All right, and explain what that's telling you. All right, so give y'all 1 minute to do that. Okay, so calculate f of 0 using that formula. That's super easy. And then tell me what that means. Okay. So you don't even really have to almost write anything down. Okay, that one's so straightforward. Okay, so what was that? What was f of 0? 78, right. Okay, so easy, right? When you plug 0 in for x, you're obviously going to get 78, right? Okay, what is that telling us now? So what does that mean to us? No, it's not the number of dropouts. You got to read carefully there, Zaman. It's not the number of dropouts. It's the what? Life expectancy. So in 1990, you got that part right. What was the life expectancy for female dropouts? 78 years, right. Okay. So this is women, all right. So they live a little bit longer than men. So in 1990, for high school female dropouts, their life expectancy was 78 years. Doesn't sound too bad, 78, okay? Not so bad, right? Okay. So if you were a high school dropout at that year, you could have expected to live 78 years, okay? All right. Now, however, what is the average rate of change from, here's the graph, by the way, of that function. What's the average rate of change from 1990 to 2015? The average rate of change. You don't have to do any calculations here, though. All right? You don't have to remember the average rate of change formula because, again, this is a linear function. So you know the average rate of change is the same as what? The slope. What was the slope? Minus 0.22, right, okay? Because this was a linear function, you know that the slope is the same as the average rate of change. It's minus 0.22. That number is a little bit more disturbing, though. What was that telling us, okay? So what's the interpretation? What's the last thing I've got to write in the notes for today? So what does that mean? So on average, okay, the life expectancy is it going up or down? Down. Darn, that's bad, right? So the life expectancy is decreasing by how much? That's right. I don't have to put decreasing by a negative amount because decreasing means it's negative. So it's decreasing by 22 years per year. So every year, okay, every year since 1990, the life expectancy for female high school dropouts has dropped. Okay? Wow. Okay? That's kind of bad news if you're a female high school dropout. Your life expectancy is going down. Okay? In fact, what has it gone down to by this year? Yeah, it's just a little bit bigger than 72. That's a little bit depressing, isn't it? Okay? You don't want to be a female high school dropout, okay? Because your life expectancy is going down, okay? All right. Well, average rate of change, easy to calculate for linear functions because it's the same as the slope. But we're not always dealing with linear functions, all right? So we have to look at some examples where our functions aren't linear, okay? All right. Yes?
I have a question, sir. I went to the review the other